Alright, so welcome back to the video everyone. Now that we are one level above in our data science journey and have already completed the first two topics, so I always feel good striking out the topics that are completed. Now I don't know about you guys, but for me it kind of gives me a sense of achievement, a feel good factor. So I always prefer striking out the topics that I've completed. Anyways, now that we already have built our first model, linear regression, so it's time to learn the second approach, that is logistic regression. So in this video, we will be covering logistic regression concepts, then logistic regression with more than two classes, and then in the end, we'll do an assignment in R, where we will build logistic regression model. So without further ado, let's get started with our first topic, logistic regression concepts. So in logistic regression, our response variable is qualitative and has two or more levels. Mathematically, formula for logistic regression is shown here. Here P is the probability of success. The left hand side in the above equation is called log odds or logit function. The logistic function is a sigmoid function and will always produce an S-shaped curve as shown in the figure. So regardless of the value of x, we will always obtain its value between 0 to 1. Now logistic regression may classify the observations to a particular class if the value of log odds or logit is greater than 0.5 and to another class if it is less than 0.5. So that is how class assignment works in logistic regression. Now just like linear regression, we will follow these steps here as well. Recall in linear regression, we used ordinary least square method to estimate the coefficients. So here we will use maximum likelihood function. The formula is shown here on the screen. Again, don't even try to remember this. Just have a look at it and move on. Now let me just give you one example how this works. Let's say you get messages in your inbox and you wish to classify the messages as spam or not a spam. When we do logistic regression, it will check if a message is real, then it will return 1, otherwise it will return 0. But there could be n number of coefficients for which this is true. So we will choose only those coefficients for which maximum likelihood function is maximum. So that is how we use maximum likelihood function. If you recall, we had seen the cost function in classification setting when we were doing introduction to modeling. This cost function can be derived from maximum likelihood function. Actually, maximum likelihood function is a generic approach used for many statistical methods, and we can prove mathematically that there is a relationship between MLF and cost function. But for obvious reasons, we will not go into the details of it. Remember, we want to keep things simple. So the cost function that we use for logistic regression is shown here on the screen. It is given by j theta. Again, you don't have to remember this formula, just have a look at it and move on. Now if you see the below figure, it says that in short, we are maximizing the likelihood or minimizing the negative log likelihood. So either you maximize the likelihood or minimize the negative log likelihood. Both are same, which in turn means minimizing the cross entropy or cost function that can be calculated by dividing the negative log likelihood by m. So that is how we estimate the coefficients using maximum likelihood function or the cost function. Now the second step is to check if there is a relationship between x and y. Many aspects of logistic regression are similar to linear regression, such as we find z statistic here and then we find the p-value. And then based on the p-value, we conclude if the probability as per the above equation is dependent on the predictors or not. So that is how we find out whether there is a relationship between x and y or not. Now in the third step, we perform the variable selection. Now we will see two common regularization techniques, also known as shrinkage techniques. We will see these techniques in reference to logistic regression. However, it can be applied to linear regression as well. Recall that we had seen different methods of variable selection in our previous topic, linear regression. There we had covered forward selection, backward selection and mixed selection. In this topic, we will cover ridge regression and lasso regression. And dimension reduction, as we know, is a different topic altogether, so we will see it in our next module. Now the first topic is ridge regression. Ridge regularization works by introducing a penalty term to the log likelihood function. Recall that we are using maximum log likelihood function to find our coefficient in logistic regression. So we modify the maximum likelihood function and introduce a penalty term in it. The idea of imposing the penalty is to reduce or shrink the less important coefficient values near to 0. Basically, we are trying to nullify the impact of less important coefficients. Now, as you can see on the screen, this is the modified equation that penalizes for allowing to have more variables. Lambda is a penalty parameter and beta j square is the penalty term. Now it is important to note that as lambda increases, bias increases, and as lambda decreases, variance increases. So we will have to do a trade-off between bias and variance and find an optimum value of lambda. So for this purpose, we use cross-validation. Now cross-validation, sometimes also called as rotation estimation or out-of-sample testing, is a statistical method used to estimate the accuracy of machine learning models. Don't worry, we will see cross-validation in detail in our last topic of this module, that is resampling methods. For now, let's move on to the second technique of variable selection, that is lasso regression. Now, why do we need lasso regression when we already have ridge regression? Because one major drawback of ridge regression is that in the end it will contain all the variables. As penalty term can at the most shrink the coefficients to near 0, but it will not set any of them exactly equal to 0 unless lambda is equal to infinity. Now this may not be a problem for prediction accuracy, but for interpretation it could be if p is large, that is number of predictors. So this issue is overcome by lasso regression. Now in lasso regression, the only difference is that the penalty term beta square j of ridge regression has been replaced by L1 norm beta j. Now you may ask, what is L1 norm? So we don't have to go into the details of it, just understand that there are two forms of penalty, L1 norm and L2 norm. L2 norm penalty was used by ridge regression and L1 norm penalty is used by lasso regression. However, if you are very keen about it, then just Google it, you can easily understand it. But as it is not required for us, so I am skipping it. Now this penalty term also shrinks the less important coefficients, but it can even force it to be exactly equal to 0. Hence, much like other methods such as forward selection, backward selection or mixed selection that we saw previously, this will also result in lesser variables and hence would result in ease of interpretation. So that was all about ridge regression and lasso regression. Now let's move on to the fourth step, that is model accuracy. Here we use the misclassification error rate or can also use deviance to assess the model accuracy. So we create a table called confusion matrix. Here the diagonal elements are the correct classification and off-diagonal elements are misclassifications. So we take the sum of diagonal elements and divide it by the sum of total elements to calculate the misclassification error. Alternatively, we can use deviance. We have null deviance, which is the response predicted by a model with nothing but an intercept. Then we have model deviance, which is the response predicted by a model on adding independent variables. Now if the model deviance is significantly smaller than the null deviance, then one can conclude that the parameter or set of parameters significantly improve the model fit. So that is how we assess the model accuracy. Now once the estimates of the coefficients are found, then we can simply plug them into our model and find the probability using the above equation. So that is how you build a logistic regression model. Now there are times when we wish to classify a response variable that has more than two classes. And in such cases, extension of logistic regression is possible. Let's say we have survey results for a product as good, bad or excellent. So in this case, we can use one versus all approach. It involves splitting the multi-class dataset into multiple binary two-class classification problems. Then create different models for each problem and then select the best model. So as you can see on the screen, we can split the above problem of survey results into three binary problems. Problem 1 has categories excellent versus good, bad. Problem 2 has categories good versus excellent and bad. Problem 3 has categories bad versus excellent, good. Now we will create different models for each category, and then we will select the best model for each of these categories, and that will be our final model. So don't worry, this can be done easily in R, but this is a very rarely used approach. We use alternate approaches like linear discriminant analysis that we will see in the next module, that is advanced modeling, or multinomial logistic regression that we will see in the later part of this module. So that is how you perform logistic regression for more than 2 classes. Alright, so that was all from logistic regression. So in this video we have covered logistic regression and the steps that are involved in it. We also studied cost function, maximum likelihood function, etc. And we also touched upon multinomial logistic regression. And now we will move on to the next part, that is assignments in R. As I said earlier, there will be 2 assignments. We will first build a logistic regression and then we will perform variable selection. So let's get straight into the assignment now. So alright, I'll catch you up in the next video. See you.